Welcome to the first lesson. Here's the first lesson for Mod 1, Chemistry and Atoms. So this is a science class. Good place to start would be to define science. Science is a systematic approach to solving problems. And we'll learn later about the scientific method. That's the method behind science. Primary types of science, these are the big three in natural sciences: biology, chemistry, and physics. There's others: oceanography, geology, and so on. There's also social sciences. Social sciences are inherently different than natural sciences. Nothing wrong with social sciences. It's just for them, they rely on different things. For natural sciences, it's about data and reproducibility. And it's actually a lot simpler than the social sciences because there are fewer variables. Something like human nature or human behavior is very difficult to deal with and experimentally determine. Whereas for chemistry, every time you take a piece of sodium and throw it in water, it's going to explode. No question. For human behavior, let's say I get in trouble with my partner and I get out of it by buying her flowers. It's not going to work the second time. Maybe it will, maybe it won't. It depends. That's kind of the difference between natural sciences and social sciences. This is a chemistry class. Chemistry is the study of matter and how this matter changes. And that's a big piece of the puzzle here, because everything you can touch, feel, hear, and see, well, hear is sound, but anything that makes noise is made of matter. So before I go on, let me talk to you about a really dangerous chemical, dihydrogen monoxide. So a little bit, if you inhale a little bit of it, it's going to kill you. It's in acid rain. Nazi Germany was very adept at using it, and it's found in chemical and biological weapons. It's also in nuclear power plants. Military spend billions on it. It's also a very powerful greenhouse gas. It's thought to cause about 80%, depending on the climate model, of global warming. Should we ban it? Well, I was playing a trick on you. Dihydrogen monoxide is H2O, it's water. And everything I told you was true. If you look at this, this is what drowning is. Inhaling a little bit is drowning. Rain is made of water. Nazi Germany used U-boats or submarines a lot. It's found everywhere here on Earth. Power plants, yep, using animal research, you got to water the animals. The Navy, for instance, has spent $1 billion. Water vapor is the primary greenhouse gas of the Earth and is thought to be the reason behind global warming. Well, people believe that carbon dioxide, the idea is carbon dioxide forces more water to evaporate, and then the water is actually what does the global warming. And so that's another reason to study science, so that people don't pull the wool over your eyes. If you're knowledgeable, because knowledge is power, and if you have the knowledge, you have control over a lot of things. And people, on the other hand, people will use your lack of understanding as a method to control you as well. So let's look at this. Which of the following is not organic? A flower, a lump of coal, or a coral shell? Well, it turns out that organic means carbon containing, so coal and petroleum are organic. Coral shell is a mineral. It's made of limestone, so it's not considered organic. So even though coral was living at some point in time, it's a mineral, not organic. So there's another thing when you learn about science. Organic, maybe you thought about organic in terms of the farming techniques. That's a legal definition. Science definition, it's carbon containing. And we talked about science, so here's a scientific method. And this is how I define it. To simplify it, there are four main steps: observation, hypothesis, experiment, and theory. And let's look at observation. These are data, and there are two types of data: qualitative and quantitative. Qualitative is idea, quantitative, quantity, is number-based. Once enough observations have taken place, a scientist or individual can form a hypothesis. This is a guess. And then experiments are used to test that hypothesis, and enough hypotheses are supported by experiment, that can become a theory or proven fact. So theory, after it's repeated enough, you can get a pretty solid theory. Theories can also be wrong. So for instance, the theory that there are 4 elements, earth, wind, fire, water, is a pretty solid theory. It explains a lot of phenomena. It explains by why wood can burn and ashes of wood cannot, because all the fire has gone away, for instance. That's wrong. I'm not going to tell you that it's right. It's wrong. Theories can be wrong. There are some theories that are pretty solid, like atomic theory. Atomic theory saying that all matter is made of atoms. And germ theory for diseases rather than bad spirits causing disease. Those are pretty solid theories. There are many theories that we have today that need to have work on them. For instance, our understanding of the cosmos right now, of the continued expansion of the universe, we don't really understand what's going on. More information will come out of this. And we can skip this and go to a law. A law is just a summary of observations. For instance, the law of gravity. What goes up must come down, right? We can do that all day. You can throw sticks, stones, balls, up, down, all day. They all come back down to Earth. But you can break the law of gravity, right? Rockets can't escape the Earth's gravitational pull. Ergo, they break the law of gravity. Another thing about science is it's tentative. So this is not ancient Greece. This is contemporary times. Contemporary times, science is based off of experimentation, not off of philosophy. And when there are data that contradicts the accepted theory, the theory needs to be changed or thrown out. So old theories like the earth, wind, fire, water theory of the Greek elements does not apply anymore because it's been experimentally disproven. Science is tentative. This is very important. Then there's technology. Science, to me, the way I describe it, science answers the question why. Why do electrons fly a certain direction when there is an electrical current applied around them? Why does it do that way? Well, then technology answers, well, how can we use that, or so what? So then technology for electrons flying in an electronic field, you can use it for like a television set, for like a TV tube, for instance. So then technology applies the science to something useful. The science answers the question why. And back to chemistry. Chemistry is the study of matter and its changes. So this is the center of chemistry. So biology studies living creatures, physics studies the physical world, chemistry studies matter. And what is matter? Anything that has mass and volume is matter. Mass is the amount of matter you have, volume is the amount of space that it occupies. There are some things that are not made of matter that we can measure. Energy is one, light is another one. Light is not made of matter. Emotions are also not made of matter. So emotions, you cannot say, give me 15 grams of aloha or 20 grams of love or 15 grams of sadness. This doesn't work out. Ergo, feelings are not made of matter because they don't have mass and they don't have volume. Now there are 4 fundamental forces. First one, gravity. It's very weak. It's positive. It's ever positive. So that means that even antimatter will have gravity with matter. Electrostatic. This is actually what chemistry deals with, is all electrostatic forces. Positive, positive, negative, negative charges repel. Positive, negative charges attract. And nuclear weak actually turns out to be electrostatic. It's what holds quarks, which are building blocks of protons and neutrons together. Actually, it turns out, like I said before, to be electrostatic. Nuclear strong, it's what binds the nucleus together. So the nucleus has protons, which we'll learn later, in the center, which are all positively charged, and the nucleus wants to fly apart, and the nuclear strong force keeps it together. Some people consider this to be 3 fundamental forces because electrostatic and nuclear weak are the same. Some people include dark energy in with this, but dark energy is the force that seems to expand the universe more. So you'll hear from 3 to 5. I'm going to stick with 4. Mass versus weight. So remember, mass is the amount of matter, but that does not change. You can go to outer space and you can become weightless, but you do not become massless, because weight is just mass times gravitational force. So chemistry is the study of matter, so we organize matter, and we organize them by properties. First, we're going to talk about physical properties. You observe them without changing the substance. So for instance, color. I'm wearing a black shirt right now. You can observe the color of my shirt without changing the shirt. Then my shirt is also flammable. You can observe that. That's a chemical property because by burning my shirt, you turned it into something else. Density, conductivity, melting point, so phase changes, these are physical. Magnetism, these are things you can explore without changing the substance. Now look at here, the color here of the copper wire, the reddish color is a physical property. And here we have on the right, there's iodine, vapor forming iodine solid. A change in phase is a physical change, not a chemical change. It's still iodine. Now chemical properties, this is the ability of a substance to change into something else. And things that change easily are reactive. On the other side, things that do not change very easily are unreactive or inert. So oftentimes when there's a chemical change, there's a physical change too, right? So you take a piece of wood, it looks brown, you burn it, it turns black. There's a chemical change and there is a physical change too. So understand that many times they go hand in hand. And some things are stable and inert. So iron is reactive, it rusts. Gold is not very reactive, it lasts for a while. So when you give a ring, we give rings in our culture as a remembrance. To give a ring for a symbol of your love, would you give a iron ring or a gold ring? Can you imagine that? It's like, my darling, as a undying symbol of my love and affection, I present you this iron ring. And she may say that, so your love is as good until it becomes all corroded and flaky and breaks away. That wouldn't be a good symbol in our culture. We want gold because gold does not react. So that's the importance of that. And it's not to do with cost either. The most expensive metal is weapons-grade plutonium, but that's toxic. So we wouldn't give rings using that. So digestion, eating your breakfast, lunch, dinner, and then your body digests it. Is this a physical change? Only a chemical change, neither, or you can't tell. It turns out that digestion is a chemical change. Your body chemically converts things into useful forms. So another thing with this class is we introduced you to the metric system. So the metric system is an engineered system. This is different than the American/English way. Metric system is everything is based off of a 10. There's a few basic relationships and everything else is based off of 10. So for instance here, comparing the two scales, here's a liter versus a quart. A liter is a little bit bigger than a quart. Quart, there are 4 quarts to a gallon. A pound versus a kilogram, there's about 2.2 pounds on a kilogram, or about 450 grams, or 1/1000th of a kilogram in a pound. And a centimeter and an inch, actually an inch is defined as 2.54 centimeters. And here are the metric units. For mass, the amount of matter, gram. Length is a meter. It's, well, I wish I could demonstrate to you. It's a little bit longer than a yard. Time is second. Temperature, Celsius. Amount of matter is the mole, which will come in later. And ampere is a current. A lot of these terms are based off of water. So gram and Celsius, so 1 milliliter of water is a cubic centimeter. So a cubic centimeter of water is a milliliter, which is a gram. And water boils at 100 degrees Celsius and freezes at 0 degrees Celsius under 1 atmosphere of pressure, or sea level here on Earth. And we can take simple terms and then add to have big ones. So kilo, that's 1,000. Mega, million. Giga, billion. Or tera, trillion. And then you can go smaller as well. Deci, centi, milli, micro, nano, pinko, femto, natto. That way you can demonstrate things that are big and small. So looking at this picture here, using mass in kilograms on the right side and size in meters on the left side, We can talk about things that are really, really tiny, like atoms, and really, really big, like planets and stars. And using the same units, using meters and kilograms. And then there's us, humans, in the middle. How many centimeters are there in a meter? Well, how many 1/100ths are there in anything? There are 100 1/100ths, so 100 centimeters in a meter. And also, let's talk about the states of matter. Solid, liquid, and gas. Solid has a definite volume, definite shape. So solid, so I'm going to hold up an envelope here. This is a solid. It has a defined shape, a defined volume. And a liquid, here's a liquid right here. I'm going to take a sip. And liquid has a defined volume, but the shape changes. The shape will change depending on the container. And gases, air, I'm breathing air right now. Air is a gas. It has not a set shape and not a set volume. So gases are the least defined state of matter. Here's a picture of that. Solid, you can see it's very orderly. Liquid is a little more random, and gas is the most diffuse states. Condensed states are often referred to as solid and liquid are condensed states. So let me explain this backwards and forwards. Heterogeneous mixtures, these are not uniform mixtures. So most things are heterogeneous mixtures. I am a heterogeneous mixture. So my eye is different than my teeth, is different than my lips, is different from my hand. You can take something like me, like my blood, and you can take blood and turn it into uniform mixtures. So blood, for instance, has plasma in it. Plasma is a uniform mixture, blood plasma. That's a homogeneous mixture. Likewise, you can take milk from a cow. Milk from a cow is a heterogeneous mixture. It separates. Cream on the top, milk on the bottom. The top is different from the bottom. When you go to the store, you buy homogenized milk. That means the milk on the top is the same as the milk on the bottom. And heterogeneous mixtures can be broken down into homogeneous mixtures, and then that can be broken down, homogeneous mixtures can be broken down as pure substances. And pure substances are either compounds or elements. Compounds are a combination of elements, and then elements, these are the basic building blocks. We have 116 elements right now. 117 is being confirmed right now, maybe will soon be confirmed as 117 elements. But pretty much everything in the universe is described by 116, 117 elements. So that doesn't seem very much, right? The entire universe. But think of it this way. There are 26 letters in the English alphabet, and from those letters you can make words. Words are kind of like compounds, right? Combination of letters, combination of elements. And then those words can be used to make statements and sentences. Those are sort of like homogeneous mixtures. And then you can mix them together to create stories, the heterogeneous mixtures. So the English language with 26 letters, you can tell an infinite number of stories using those 26 letters. Likewise, imagine if you had 116 letters to deal with. It would be a lot more complicated. That's the world of chemistry. So let me explain it the other way. I talked about it with heterogeneous mixtures. We can start with elements. There are 116, 117 elements. You can join those together to form compounds, which are a combination of elements. And those you can mix together to make either homogeneous mixtures, which are uniform mixtures, or heterogeneous mixtures, which are non-uniform mixtures. And let me give you an example of a few heterogeneous mixtures. The ocean is a heterogeneous mixture, right? Because or at least at the beach, there's sand and water and seawater. And sand is different than seawater, and they coexist. But seawater, assuming that it's relatively clean, depending on how you like to swim in Ala Moana, it's not always super pristine there. Seawater is a homogeneous, uniform mixture, and then that can be broken down into salt and water, which are both compounds, and salt can be broken down into sodium and chlorine, two elements, and water can be broken down into hydrogen and oxygen. And if we go further down, the ultimate unit of an element is an atom, which we'll get to later. So what about beer? Let's talk about beer, for instance. Is this a homogeneous mixture, heterogeneous mixture, compound, or element? Turns out this is a trick question. If it's flat beer, it's homogeneous. If it's beer with foam on it, it's heterogeneous because the foam is different than beer. So let's talk about energy. I have 7 nieces and nephews. As this is being recorded, one's on the way. They have a lot of energy. What does that mean? Well, it means they could be doing work. They could be washing the dishes, they could be mowing the lawn, but they're not. They're kids and they're playing. So energy is the capacity to do work. And there are 2 main types, kinetic and potential. Kinetic is energy of motion, potential is stored energy. There's other types, so electromagnetic, this is the carrier of the electrostatic force. So light is another form of energy. But typically you deal with kinetic and potential. And heat is kinetic. And a candy bar, so I eat a candy bar, has 100 calories. What type of energy is this? This turns out to be potential energy. It's stored energy. After I eat the candy bar, my body can access that energy, well, after it digests it. Now we're going to move on and talk about atoms. So here is a piece of platinum, and if you take a look at that piece of platinum, you can see these bumps on the surface. So this is a new thing, actually. This is, well, from 1970 we've been able to image atoms. Before that we could not see them individually, so we had to understand that and look for evidence for their existence. So we're actually very fortunate that we can talk about atoms and actually be able to count them one by one, which is a rather unique thing compared to the history of science. So let me go over the thinking. This is a little bit of science history lesson. Not too much, don't worry, this is still a science class. But first proof of atoms, which we'll get to, is the law of conservation of mass. This says that matter is not created or destroyed. So for instance, water evaporates, doesn't vanish, it just changes form. Or you can take a candle and burn it and it seems to disappear, but if you gather up all the reactants and what it turned to with the products, if you measure them carefully, you'll find the same amount. Lavoisier, a French nobleman, is the one that did this, and he had an interesting experiment where he did nothing but drink milk to see if he could survive, and it turned out that he could. That surprised people today. He and his wife did a lot of experiments here. So let me give you another example. If you take cinnabar, which is mercury oxide, and you can break that apart into mercury and oxygen, and that will equal exactly what you started with. So matter is not created or destroyed during a chemical process. Then next proof that brought up atoms was law of definite proportions. So compounds are made of elements. Remember, compounds are a combination of elements, but they are made always in the same proportion. So water is always 11% hydrogen and 89% oxygen by mass. So that is always true. There's also, so here you can take lead and sulfur, and to make lead sulfide, it's going to always be in the same ratios. And if you have extra of the other, then you just end up with extra at the end. And there's multiple portions, so water can make is made of hydrogen and oxygen, but you can also make hydrogen peroxide. So 2 elements can make compounds in different numbers. So this is the law of multiple proportions. And for instance, the oxides of nitrogen, there are several different examples of different types of oxides of nitrogen. This also illustrates the law of multiple proportions. So Dalton's atomic theory, Dalton went one step further, and he said that atoms are made of these tiny things called atoms. And this was a hard sell. So Dalton told his friends, hey, look, the universe is made of these really tiny little things called atoms that you can't see. We can't see them, but here's the proof for them. And he talked about definite proportions, conservation of mass, and multiple proportions. But he took the next step, and he said that atoms of an element are all alike, but an atom is the ultimate unit of an element. Each element has the same atoms, and they're all the same, but different atoms have different elements have different atoms. This is mostly true. That turns out to be wrong. Dalton also thought that atoms were solid spheres, kind of like the playpen in McDonald's, like the ball pit. He thought that atoms were like that. Atoms turn out to be mostly empty space, which we will talk about later. In the periodic table, we have many elements, over 100. A few of them are man-made, meaning that they're not found naturally in nature and we make them. And like the element 117 I was talking about, if it does exist, it doesn't exist for very long. So it's not going to be like another element like gold or iron. It's only going to exist for a very short period of time. In the periodic table, it's arranged in the periodic table because of properties, which we'll talk about later. And vertical columns in the periodic table, they have similar properties. We call those families or groups. So here's a periodic table of the elements. And I'll tell you a little story about myself. When I studied chemistry in high school, I looked at the periodic table and I thought, like, this does not look really good. I'm going to go through and look at the properties and come up with a new, better way to do it. And I actually spent some time looking through books and comparing properties and rearranging the periodic table. And it turned out in the end that I think that this is the best way to do it. You're welcome to go through and try it. It was a fun exercise, but you can take my word for it. But please, by all means, try it. It's fun. And then, so let's talk about the zigzag line. So there's the zigzag line right here. What does that zigzag line mean? Well, to the right of this zigzag line, there are nonmetals, and to the left of the line, so this here, and these here, these are all metals, and down here too. These are all metals. But then there's this area in between that's kind of both. These are called semiconductors or metalloids that are kind of like metals, but not completely like metals. They're kind of like nonmetals too. So these are kind of in between. So nonmetals tend to be brittle and insulator, so they do not conduct electricity. Metals tend to be ductile, which means they bend, and they tend to conduct electricity. So if I had a charge here in my back wall at home, and I took my envelope and I touched the wall, would I be shocked? No, I wouldn't, because paper is made of carbon, oxygen, and hydrogen, all nonmetals. But if I took, I don't have a piece of metal handy, but say this pen was made of metal and I touched the wall, I would get shocked, because metals, this is plastic, it's not a metal, but metals would conduct electricity. And silicon, for instance, is a semiconductor. So silicon generally does not conduct electricity, but if you apply 5 volts to it, it will conduct electricity. And that's the basis of our computer systems right there. All our computer systems is based off of that simple fact from silicon. So I've talked about this already. Another thing to think about, so normal cars are usually made of metal, at least the hulls. Corvettes are made of fiberglass. And when you see a Corvette into a car wreck, they shatter, whereas normal cars tend to bend. So that's another thing. You can look at metals. They tend to be ductile, and nonmetals tend to be fragile. Now I'm going to go on and talk about the origin of the universe. And so we're studying about matter. A logical question would be, where does matter come from? And there was a massive expansion event about 13.7 billion years ago that created what we can observe in the universe. And this expansion event from energy turns matter. So matter cannot occupy the same space at the same time. But energy can. Light can be in the same space at the same time. So you can put everything in the universe into one point. And then this one point expanded and formed atoms. And then after a couple 100,000 years, the universe cooled enough to form stars. And then stars are nuclear furnaces, and these stars burned. Eventually they formed iron, and for certain stars 3 times the size of our sun or larger, they would type to a supernova and form other elements. And so a lot of the elements that are in us, well, except for hydrogen, are from stars. We're made of stardust. And anything higher than iron is made, higher than element number 26, is made in a supernova explosion. And then these exploded to form other stars. The Sun, for instance, the Sun is a third generation star, which means the Big Bang happened, a star formed, that blew up, another star formed, that blew up, and formed the Sun. So we're at generation number 3. So here's the pillars of creation. This is shows how some stars are being formed. And a note to people: these are NASA images, and what's nice about NASA images, they don't have copyright. So if you ever want to use images, NASA images for anything, there is no copyright. You're free to use them as much as you want. Here is our Sun. Our Sun is a star, generation number 3, and this is a galaxy. It's a spiral galaxy, and there are hundreds of billions of galaxies from what we can tell in the cosmos. And each of those galaxies contain millions to hundreds of billions of stars, depending on the size of them. And there's a lot of matter in the universe, is what you can take home from this. So you can see all these different galaxies across the cosmos. And this here is a planetary nebula. This is what we're going to end up. Here's another picture of a planetary nebula. Eventually the Sun will expand. It won't explode, at least in a Type 2 supernova. It might explode in a Type 1 supernova over time, but this is what the solar system will eventually look like. But now let's talk about the Earth. The Earth formed about 4.6 billion years ago. And the planets and stars, they all look like spheres. Why are they spheres? Because they're formed by gravity. Gravity forms them. Earth is slightly oblate, but we're mostly spherical. And here's the Earth. We'll talk a lot about the Earth in this class. The Earth is a very unique place, and we will continue to talk about the Earth in mostly the second, kind of the second half of the semester. We'll talk a lot about that. But that concludes the first lecture.